Actually, the subject we are covering right now is so important to understand the overall idea of the solid mechanics of our strength material. The main reason is that through this solid mechanics, what we're gonna learn as an engineer, mechanical engineer, actually we are able to design a structure which will be subject to a lot of mechanical or thermal load. Uh, and how can we design structures? Well, we first need to understand the failure of the material. To understand the failure, the critical point is the understanding stresses in a body. So to understand the stress, this is the we are covering the subject of a transformation of a stress. This is a core part of a stresses. So I shared the Excel last week, and then please let me know if you have any problem in Excel or sharing. Uh, Sometimes I miss something is not the right way. But anyhow, you can always Katalog doesn't work right now. You can We can chat through a chat of this Zoom. I hope that this screen is well shared, right? Okay. Now, this is the one shared, and then you already have this Excel. Uh, I highly recommend you to develop your own Excel. Uh, well, the Excel tool itself is so essential for student like mechanical engineer. Anyhow, the Excel is the our favorite tools. So we learn the all the transformation, how we transform the stresses in terms of original stress component and also a function of a sinusoidal function, cosine and sine. And notice that there's always a cosine square, sine square, and then cosine, sine, always two terms. And we simply put this one into Excel as a function of a theta here in the degree. And then cosine and sine, we can easily get the value using the Excel function. Now the sine sigma x prime, this one, again, this is like that. Sigma x cosine square, and then sigma y and sine, and sigma xy and cosine sine. Here is the cosine and sine is represent, we just define a cosine sine like that. And original sigma x, sigma y, and sigma xy is we define here. Okay, I just want to remind you. Now we simply plot these three components. You can see. Okay, I think this one. Okay, same one, but with no, this one is the from 0 to 180 degree. We can simply extend from angle from 0 to 360. Let's do that. To do so, okay, the 360 here. And then the reason it doesn't automatically fill this blank is that the cosine is simply, as you can see here, cosine is only defined from here to there. So we need to extend the name assignment up to here. So simply you select like that and then go to create from selection and top row. And then we are asked to replace existing cosine and say yes and say yes and say yes. Now you can see that the cosine here we have extensions. Now let's try to copy this one. Oh, sorry, I didn't extend this data. Okay, so this way, as you can see that we can very conveniently work with the plot and then also work with a vector and etc. So this one is also can be extended like this and like that. And also, I mean, we don't have to do it this way, but I just like to show you one way to cover the range to plot. Okay, so simply we cover from 0 to 360. Uh, and now, very importantly, as in a homework, what we were trying to observe was that sigma, uh, actually the x prime plus sigma y prime, oops, y prime. So this term, you can simply say sigma uh, x prime and plus sigma uh, y prime. Okay. Now, as you can see that we what I did was we just add these two. As you can see, we just add them. And as you observed from a homework, this value, summation of x prime, y prime, the value does not change. Uh, well, we need to understand why, but it's very important to observe. And actually, this term, not just this one term, okay, I like to add here from here to this one, and you can plot them. Uh, okay, so you can plot them. As you can see, this is a constant. I will just copy this one to here so that we can see along the angle variations, we can observe that cosine and sine, I mean the sigma x prime, sigma y prime, and also summations. I just like to add the x and data level. Oops, not this one. Uh, legend, so that we can see which one is which. And this one is simply, we can say angle. As an engineer, it's extremely important to show all the results using the graph. This is much more powerful than just a number. We can say stresses. Okay. Now, actually, the go to previous vector. This one, uh, I'm trying to get back to a vector transformation. This is a force. Okay. We simply know the vector transformation fx and fy and cosine theta, sine theta, and there's a minus and plus. And this was the what we did last class. Now I'm trying to explain why and what's the meaning of this value which does not change along any angle. Now, even for the this vector, we can observe very similar quantity such as. Okay, before I show that, I'd like to ask you one point. Let's say we have a certain body, we have a certain force like this. Now, this is the x-axis and the y-axis. And we certainly have this much component. Again, we like to remind ourselves of the definition of a force transformation. What does it mean? Means that if we have another coordinate system like that, this is x prime and y prime, and this is a theta. The force transformation means that we will have another component, new component for this newly defined coordinate system. So this much will be a fx prime and this much will be a fy prime. So this graph or this formula shows the how this term, how these two values will vary along with this theta. Okay, that's the concept of the force transformation. The purpose of me explaining this one is to help you to understand the stress transformation. So now, let me ask one thing. Regardless of this coordinate system, what quantity does not change? Which one? What does not change? Well, simply this magnitude will remain the same, right? The magnitude of the vector will remain the same. So we can simply say, uh, I just like to know this will be a fx prime plus fy prime. Actually, the magnitude, we need to have a scale and plus scale like that. And actually, we need a square root. That's the term we like to calculate for each angle. Now, again, like this, equal. We probably didn't define this term, so I just click this one and then click. Instead of using the name, we can directly define the cell like this. So this magnitude is like that, and we can simply copy and paste. As you can see, or as we can expect, the magnitude would not change, and we can simply add this term from here to two columns and insert and plot, and we simply copy and paste again here. And now, as you can see that this one, we can observe that along this angle from 0 to 360, each component of x prime, fx prime, and y prime will change like that. And also notice that this at zero angle, this term is the 10 and this term is the 20. That is exactly same as this guy. Initially, at the theta equal 0, the term was given as the 10 and 20. Now this 10, you can see how it change like that along with the angle. And this 20, you change it. But again, the what it does not change is the magnitude. Magnitude, we know that the vector, since it's a vector, magnitude of vector would remain the same, does not change. We know that, right? Amplitude or magnitude of this vector. And then we simply add this term and then we confirm that. That's the exactly same concept as the invariant. We call invariant. Invariant. The invariant means that something which it does not change. So we call them invariant. Very important concept in the vector. Now, for the stress transformation, exactly same concept for these two terms is called invariant. Summation of a sine and sorry, sigma x prime and sigma y prime, this term does not change. So we will call it's an invariant. Now, as you can see that this is the magnitude, so you need a scale, and root. But here, we just sum, plus. Uh, we don't need a scale, right? Uh, And as you can see from this, if we add them, we can easily observe that if we add them, let's see, this term disappear, right? And then this term, as you can see, cosine square and sine square gives us a 1. And this one, sigma yy, and cosine. So actually, we can see that if we add them, we can simply have a sigma xx plus a sigma yy. See, add them, giving us this two same sigma x plus sigma y. So we numerically confirm that. We also graphically confirm that. So that's the concept of the invariant. I know this is a very new concept to you, but just imagine the what does mean by invariant in vector. Something does not change. In this case, the physical quantity is the amplitude. Now the stress transformation is the something which does not change is the just a summation. Now there is another term actually, another invariant. Okay, this is an invariant. I will say one. Uh, Actually, there is another invariant. Uh, I will just give you answer. Answer is that 2 sigma x prime minus sigma y prime square plus sigma xy square. Uh, why I come to this equation? Well, don't ask me. If you look at this one, you put it here, you will see this invariant. So we simply follow this term equal uh, square root and then sigma x prime, oops, sigma x prime minus sigma y prime and okay, divide square, you can divide by 4 and plus sigma sigma x prime y prime. Okay, sigma x prime y prime and here and square and like this. Huh. See, we enter the formula like this, and all along the angle, this term does not change. Well, force is easy to say because this is an amplitude, and so this is an invariant. But stress is difficult to say. What is this? The just a summation, and this is the this scale. Okay. Now I'd like to give you a better idea of this term. Why this not change? I mean, you can simply put it here. Put these things here and then put it this here and this here. You will see this is exactly same term as like this. Okay, so that's why it does not change. Now, another very interesting observation we can make is that I just plot here the okay. Let's try to plot sigma x prime. Hmm? Why am I stuck? Okay. Just sigma x prime. Instead of an angle, we just try to plot sigma x and sigma xy. Okay? You understand what I'm trying to do? Sigma x prime, sigma x prime y prime. And let's try to plot that. I'm trying to have a same scale. This is a scale of 4, and this is a scale 2 and 2. So it's about the same scale. Again, what we plot here is that we try to plot this one as an x-axis and this one as a y-axis. Okay. Is giving us exactly the circles. Okay, this is a circle, and means that if this, okay, we have a very important point here. Let's say we pick this guy, and this one and that. The sigma, if theta equals zero, the sigma x prime x and 2, and this is a x prime and y prime, and this is the sigma x x, and this is a 2 and 2. Now, where is that point here? 2 and 2. Okay, this is a prime prime. 2 and 2 means that this guy. So this we know that this is a theta equals 0. So theta equals 0 here. And then along with changing, let's take a look at, there is another one at the 90 degree, 2 and 2. Where is that point? Sigma x prime is a 2 and 2. And that is the actually looks like the same position. And here 180 also same position and same position. So actually the this way try to plot another one. Mm, okay, sorry. I need to use the equations for. Well, actually, what I'm trying to give you explain is the concept of the Mohr circle. See the sigma xx and sigma xy. We have a plot, and was the original point, and then this was the x and y, and this y means that this is important, yy and xy, and xx sigma xy. And this is the, now we change the angle to theta, and we have this new point. So a little bit, the complication procedure of come to this circle in equations. Actually, here we have cosine and sine. We have an identity. Okay, this is the equation we got, right? And then cosine square theta, is the same as the 1 minus cosine 2 theta, right? And sine, this one is 2. Oh, sorry, this is a plus. That is the what we have here. Okay, that is the what we have here. Oops. Oops. Okay. So 1 minus cosine 2 theta here. And what is this? 2 times the cosine theta and sine theta. And simply this is a sine 2 theta. So using these types of identity, and when we put it here, we simply get these terms. Uh, term of this one uh, becomes this equation. Now in terms of cosine 2 theta and sine theta, this is just nothing but the mathematical manipulation. No, not much the physical meaning, but just follow the mathematical conversions in terms of 2 theta. Okay. But here, as a result, we have a very interesting terms, these two terms. Now, similarly, we can have a y prime, y prime. And importantly, sigma x prime is we have this and that. There's some minus. Again, this we got this equation from this using the sine cosine identity equations. So this is the one. Now, this term can be plotted or represented by a circle like this. Uh, there's a little bit complicated plotting procedures, but again, the concept is that sigma x prime and y prime sigma x prime. Rather than remembering this whole equation, what would be the good way to represent or to remember to understand how this angle this amplitude change? So that's why the is called a Mohr circle, and this is the definition. So simply the procedure is given like that, but it is very much straightforward. Say sigma x prime, you have a point because this is the axis, sigma xx and sigma xy, okay? And the same, this is the can be a yy as well. So let's define the x with the xx sigma xy. And then exactly 90 degree, there is a yy and sigma xy. So you can just straight line and then make a circle. That's all you need to do. Now, say by rotating 2 theta, okay, not the theta. The reason is that we have all the 2 theta. And you got the new coordinate, which can be called x prime and y prime. Now we have a coordinate. So this xx become this, xy is become like that. Okay. So like this. So no matter how we change the value, we can see that this all kinds of value just within this circle. Okay, within this circle. If we have these two terms and then circle is just the within this circle. That we confirm from this plot. We just the plot and the transformation, we can see that. Okay, so this can be called the Mohr circle. So good thing, the message we can get is that this is the maximum possible stress will be here. No matter how much you rotate it, you will have this maximum and minimum, and also maximum shear stress here. Now the invariant, as you can see, if in this Mohr circle, what is a constant regardless of all the rotations? What would be the invariant? Invariant will be this center. Okay, this is center. As you can see, so whatever you have a point here and point here, this is a center, right? So this will be a sigma xx and sigma x and y, and this is a sigma yy and sigma xy. And so these two terms and average will be a sigma xx plus sigma yy and half. That's why the two-term summation will remain the same, which is the here. Actually, if we divide by 2 and giving us the center of the radius, so this is a 2. Aha. So no matter how angle change, this position is remain the same. That's why it always a 2. So first invariant represent the center of this circle. And how about the second invariant? Second invariant, and from this circle was not changing. The second one, uh, again, no matter how we change this one here, the radius, okay, this radius is always remain the same. So how we calculate the radius? Radius is simply this is a half, and this is a radius r, and this one sigma x minus sigma y divide by 2, right? Divide by 2. So this is the length, and this is the sigma xy. So if we have a scale and root and giving us a radius. So simply within this circle, regardless of rotation, the radius will remain the same. Aha. So the second invariant is that just radius. So this invariant, you can see that the first one is the center of radius, and second invariant is the no, sorry, center of a circle, and then second invariant is simply the radius. Okay, so back to the definition of a force, the invariant represent the magnitude. Now stress transformation within this circle, there are two invariant. One is the center, and second invariant is the radius. So center of the circle and the radius, they are invariant. Okay, invariant. We will further explain the physical meaning of this invariant, but right now we just observe how to calculate those invariant. At this point, we try to understand that much. Okay. Uh, The good thing with this Excel is that you giving us any value you like. As you can see that invariant or this angle variation can be automatically calculate. Let's get back to this plot. Okay, this plot. This is a real variation. Now, uh, let's try sigma xx equal 1 and sigma yy equal 1 and sigma xy equal 0. Huh? What happened? Well, 110 means that 110 stress state like this, sigma xx, sigma yy like this, and no shear. So in this case, what does it mean? Means that this is the same. Go to a circle, this term and this term will be the same and no uh, sigma xy. Actually, in the Mohr circle, you simply have a point. Okay, a little bit complicated to understand. Let's start to do a little bit easier one. And 2 and 1 is that this is the 2 and 1. So this is the sigma xx and sigma xy, and this term and sigma yy, and this is a sigma xy, and x we call x and y. Remember the procedure we explain here. We choose the xy, and then this x. We choose this x, okay, and then we choose this y, and then connect them. We just make a circle. Very much straightforward. So here we did the same thing. This is a x and this is a y with a coordinate of 2, 0, and this is the 1, 0. Okay, you can select it easily. And then next step will be the make the circle like that. Okay, so that's exactly the plot we have like this. See, this is the 1, 0, and this is a 2, 0. And if we have the another term, you can simply follow that. Now, one thing here, if we have a, sorry, it's a little too small. If we have a 2, 1, 1, let's try to plot. Okay, 2, 1, 1, 2, 1, 1. What is x? Well, simply you say 2 comma 2 comma 1 y, so 1 comma 1 comma 1. So can you plot here? Can we plot this one? Well, say this is a 2 and 1 is somewhere. This is a x and then a y, 1 comma 1, 1 comma 1. Now here, one kind of careful things that the one here, okay, one here, 1 comma 1 is the here, right? This would be the y in regular, I mean, way of plotting. But in here, one exception is that when we plot the y, this is a plus, then we go into just the opposite direction. Only sigma xy, the opposite direction. So this will be the y, okay? This is not the y. That's the only exception. Why we do that? Well, that's the definition of this complicated transformation, and we try to understand the how to understand. I mean, how plot that. So this is the x, and now we connect them when we make the circle. So now, no matter how it goes, this is a 2 theta, and then you can understand this is x prime and this is y prime. Uh, so to get the precise the value, you can easily get the idea, the magnitude. Okay, so let's confirm that one from the real circle plot. Sorry, a little bit messy here. But trust me, this is exactly same as we getting here. Okay. Uh, so 2 comma 1, I mean 2 and 1, where is it? This is a 2 and 1. Here is the x, right? This is 2 and 1. Here is the x. And where is a y? Y is that 1 comma 1. Again, 1 comma 1 is not here, but here. Why? When we plot the y point, the shear is always needs to go negative direction. And then connect that, and then we simply make this circle like this. Okay. So this from this plot is very easy to understand. Oh, when will shear disappear? We don't know this angle, but we can see, oh, this is a theta, and then this one, oh, shear term will disappear. Shear term will disappear. Uh, where could be that point? As you can see that. Somewhere here, shear will disappear, right? And then that this term 2.7 and zero point 0.4. So this will be a point, this term. This is I mean, almost a zero here. And so this term will represent this guy, and this term is represented that guy. So as you can see, this is a 130 degree, 130 degree. As you can see, this is the how we got the idea of plottings. Okay. Again, my point is that we can understand the transformations, this complicated equation. We derived from force equilibrium, rather complicated procedures like this. The concept, I'm sorry. A little bit complicated equilibrium condition like this, right? Now, the all the stresses can be uh, understood in this way using this plotting. And again, you don't need to remember all this complication. Where is that? This equation or dedication or dedication. You don't need to remember. Why you don't need to remember? Let me ask. Why you don't have to remember this? Well, answer is that simply, well, you can always open your lecture note. You don't have to remember. You just look at this formula and then this is the how the equation looks like. But the most more important point is the understanding. What does it mean? How we get this one? What does it, the way we understand and all through this planning the Excel. Now this is important to understand the concept. I will further explain little by a little more. Uh, okay, now you have Excel. You can add second term, radius of this circle. You can observe that those terms do not change. I know it's a little bit complicated, simply because it's a new concept to you, and stresses is not a vector. It is the second order tensor. Physically, a little bit complicated, but the concept is should be clear. Means that okay, the stresses are given. I will repeat one more time to clearly explain what does it mean by stress transformation. Okay. Here, okay, stresses are given. 2 by 2. Now, what does it mean? Means that these two term, we just cut here, xx, cut here, you have sigma xx, sigma xy. I mean, sigma y, yxy, xy, it doesn't matter because they are symmetry. Okay, these two terms are represented by these two terms. And then also, same here, what if we have a cut here? There will be some two component of a stress up here, and these two component will can see here. Okay, so this 2 by 2 represent internal force, and the internal force will be can be seen by this way. So actually, there will be a little bit of a vector here. We have a decomposition, and here a little bit of vector here. We have a decomposition. So, but the way we cut here and here, that's why we have a 2 by 2. Now the transformation means that the same stress here. Now we like to cut here. What if we cut here? What kind of a stress will appear? Normal and the shear. Okay, this normal and shear. So we call sigma x prime, and this is a sigma x prime y prime. How much this and how much that? That is the concept. Okay, that is the concept. And then not only that one, but also we can cut along this way. Always a two orthogonal plane, like this and like that. So if we cut here, we have a two component. So same thing. So that's the concept of this transformation. Okay, so just to understand what we review here, you don't have to remember all the equations. Why? Because you can always uh, uh, back to this lecture note or internet searching or Excel file. But please do not do not forget that the concept of this stress transformation. And one thing I like to emphasize again, so this value keep changing, but no matter how we cut, the one thing does not change is this guy, the summation. This guy and that guy, always the same value. Very interesting. Same value. Not like a vector. A vector is different, but stress, this term does not change. Another term they don't change is that a little bit more complicated, minus sigma yy and scale plus sigma xy scale. You can say the prime, it doesn't matter, right? So this term will be the invariant, this term will be the invariant. This not doesn't change. So this we call first invariant and second invariant. And the if we refer to that circle, this represent the center of a circle, and this represent what? Radius of the circle. Why so important? This invariant is why so invariant? Because the material failure will be determined by these two invariants. I will further explain that one. But please don't forget the stress, the failure will be controlled by these two terms. Not just the this term, not just the other term, always these two terms. This will determine the failure, level of failure of the composites. Okay. And say we can have a there are some example, say sigma 0, 0, 0, 0. So only sigma xx. See, no shear and no yy. This term, if you plot, you can easily plot x is a sigma 0 and x, I mean 0. Y is what? 0, 0. And what's the next procedure? We simply connect them and then make a circle. And then if you want to have a certain stress transformation at the new, and you simply 2 theta, okay? Which means that if we have a cut this one with this is the this much angle, this is x prime, this is x, and this is a theta. In using this Mohr circle, all you need to do is just get the x and y, and then rotate by the 2 theta, and you will have this is x prime and y prime, and this one will be x prime, and this will be x prime y prime, and uh, this guy, this guy, and that guy, that will be have some x prime and y prime. Okay, this is the this guy, and that is this guy. This much stress will occur, will happen on this plane with the theta with respect to x and y. Okay, that's the concept. Well, I know it's a little bit complicated, but it is natural simply because the concept is new. But you keep thinking, you try to understand. Soon you will get familiar with this concept and fully understand the stress transformation, and which will help us to understand material failure. Okay, material failure, which we didn't go that far. Okay, we didn't go that far, but remember what we have this 3-5-1 flow chart. Always, once we have a stress, we will compare with the strength. And then this strength comes from the material failure. And then you will see, we will see whether this material will fail or not. So to do so, we need to understand the strengths, and here we need to understand the stress transformation. Okay, I will make the just a little more uh, slide. You can see there is a observation of Mohr circle. Actually, we already explained about the this observation of a Mohr circle. Uh, See, we know how to pick this guy. So simply sigma is given like this, and sigma xx, xx, sigma xy, and sigma yx, and sigma yy. So from this we got this, and from this we got that. So I will just say this is x and y, and then make a circle because we have a center, we have a diameter, and we can have a circle. Now this term is a two theta. Here is the important point. Why? What happened on this point? In these two x prime and y prime, the shear term disappear, right? So this one is x prime and the shear is a 0, and same here, shear is a 0. So and also this can be a maximum possible. No matter how much we rotate, this is the maximum normal stress. So as you can see here, no matter what the stress you have, this point always they represent the maximum possible, right? This one and this one, always a maximum. So this is the maximum normal stress and also minimum normal stress here. And very interestingly, this and that is 180 degree apart. But this, remember, this is always a 2 theta. So 2 theta means that theta equal 90 degree. So if this is the sigma max, and this is the x prime and y prime, and here is the 2 theta is a 90 degree. That's why we have a x and y prime. And if we have a x maximum, this will you will have what? Always a minimum. And sigma this shear disappear. No shear. No shear means that the sigma xy this is zero axis, right? So another very important point is that this guy, when you rotate this much, this is the maximum possible shear stress here. Maximum shear stress. And means that we keep rotating, and certain axis, we have these two terms, the sigma xy, which is the maximum, okay? Maximum is that point. And also at the maximum, we have a sigma xx and yy, these two terms. If sigma xy maximum, this sigma xx and yy, they are the same. They are the same. So from this circle, we can observe a lot of characteristics, and then giving us a very interesting, very easy understanding of transformation. So maximum shear loading by normal stress. So what does it mean? Now, back to very simple case. We have okay, forget about all the transformation. I know you are a little bit confused, but just look at this very simple case. We have a bar, okay? You have a bar, and then we try to extend here. So sigma x equals sigma 0. That's it. Okay, this is the only one case. Now, what if we look at this plane? What's going on this plane? Or I would like to plot here like this. This is a sigma 0. And if we have this plane, what will happen to here? You can immediately see that there will be only normal stress. No, I don't think so. Because this guy and that guy, they won't be a force equilibrium, right? So in this in this plane, we need to have a little bit of a shear stress so that this term and this term will be in force equilibrium. So that's exactly the concept. This is a normal stress, and this is a shear stress. And that's why we have a shear term. And then we can plot this and know y here. and then we can rotate. So since this is 2 theta, 90 degree, so theta equal 45 degree, so important degree, angle. 45, this plane, 45, this shear, okay, this shear will be a maximum. As you can see, this is the maximum, and that will occur uh, at the theta equal 45 degree with respect to this simple extension. So that's why the metal always fail. I mean, we can observe that the sort of a shear failure strain, I mean shear failure. Well, that subject will be covered next time, but the uh, theta equal 45 is important in this simple case. And normal stress and shear stress, we already get the equation, but here and there we have a center, we have a radius. This is a center, we call C. This is a radius R. Radius R is like that. So this is a C. I will represent the C. And plus this is the right hand side. This one is the minus. So this one. So maximum normal stress can be calculated from this equation, and minimum normal can be calculated like that. So this one and that. This is the maximum and this is the minimum. Simply center plus radius, center minus radius. And this angle can be calculated from this formula, but it's not so important. Maximum shear stress, well, is simply the radius. Maximum shear stress is the same as this invariant, right? So R and C were the two invariant. We already observed that. So there can be many observation we can make from this stress transformation from the XL, from the Mohr circle. They are all same. And principal stress, in Korean we call 주응력. Principal stress is the one we don't have any shear stress maximum. So most circle we have always like that, and that on that is a no shear. Sigma x prime y prime will be zero, and this is always a maximum, and this will be always a minimum. So this is the 주응력 and principal stresses. And maximum shear stress, this is the one. This is the always here. This is a maximum shear stress, right? So this radius is the one maximum shear stress. And also at this point, we can say this is X and Y. Always we have a same uh, tension stresses in X and Y. From this, you can see this uh, circle. Okay, very confusing, huh? 조금 복잡하죠? 예? 그런데 복잡한 게 당연해요. 지금 이 컨셉이 여러분들한테는 처음입니다. 여러분들이 고등학교 때 벡터 처음 이해할 때 조금 혼동됐죠. 예를 들어서 스칼라, 뭐 어느 물체의 온도라든가 어느 물체의 뭐 질도, 밀도, 뭐 온도 이런 것들은 우리가 알잖아요. 피지컬 as a physical quantity로 어떤 그런 거는 이제 이지하다가 갑자기 벡터가 뭐 화살표를 표시하고 화살표가 두 개의 컴포넌트를 표시하고 이게 막 회전할 때 이게 어떻게 변화하고 애 배울 때의 어떤 새로운 세계와 지금 비슷한 느낌이 오는 건 당연합니다. 그러니까 이게 어, 우리가 보통 스칼라, 그러니까 let's say you have a temperature here. This is the uh, zero zero order we call tensor. 그러니까 temperature라든가 density라든가. 근데 여기에 만약에 우리가 force를 가했어요. We apply the force here. So force or velocity or acceleration. We call a vector, but we call a forced tensor. Now 여기에 막 바깥에 이제 힘이 가해지면 what will happen to inside? 여기에 스트레스가 이제 만들어집니다. 어, 이게 우리가 이제 세컨 오더 텐서라고 불러요. 그래서 시그마 있고 앞으로 배울 이 스트레인드 전부 다 세컨 오더 텐서예요. 그래서 이게 이해하기가 좀 어려운 게 처음인 사람한테는 당연한 겁니다. 이거에서 zero order 텐서에서부터 스칼라 이게 이제 스칼라라고 부르고 이것이 이제 보통 벡터라고 부르고 이것이 이제 세컨 오더 텐서라고 부르는데 그거는 스트레스가 그 스트레인이 있습니다. 이제 지금 차원이 한 단계 넘어가요. 또 여기 여기 또 있어요. 또 있고 또 있고 또 있고. 그러니까 피지컬 퀀티티들이 뭐 마그네틱 필드라든가 뭐 스티프니스 텐서라든가 이런 것들이 막 차원이 막 올라가요. 그래서 그 차원이 올라갈 때 이 그 트랜스포메이션, 이게 좌표계에 따라서 어떻게 되냐를 이해하는 게 가장 키 포인트입니다. So understanding transformation by the coordinate is a critical point. So don't worry too much. It's a little bit complicated to understand the second order tensor or stress which we try to plot using the circle. Well, originally those are obtained from force equilibrium, but we try to plot them using the circle, Mohr circle. But Mohr circle is nothing but this variation. We just plot them by the components. You can observe the many things. Uh, and the again the same concept as the vector transformations. Okay, so just the uh, concept of the transformation. Another thing is that temperature and density. Well, here we have a temperature. 여기에 온도가 이렇게 있습니다. 이 온도는 우리가 좌표계를 X하고 Y로 우리가 이렇게 봤어요. 그럴 때 온도하고 우리가 좌표계를 이렇게 해서 X 프라임하고 Y 프라임 했을 때 이 온도하고 어떨까요? 같아요. 그 자체가 인베리언트예요. 온도는 안 바뀌죠. 질량도 안 바뀌고 이런 것들은 영차 텐서입니다. 그러니까 스칼라양이에요. 소위 스칼라양은 들어봤을 겁니다. 그리고 이제 벡터, 그다음에 세컨 오더 텐서예요. 그러니까 이거는 여기 주로 인베리언트가 이렇게 매그니튜드라고 표현하죠. 이게 세컨 오더 텐서는 이제 두 개가 있고 이제 그랬죠. 자, 그게 지금 우리가 배운 컨셉이고, again, the equation you can always using the Excel, you can 사실 오늘 수업에 내가 좀 이 그 챗GPT로 데모를 하고 좀 뭔가 보여주려고 했는데, 어, 자꾸 얘기해서 미안한데 중국은 지금 정책적으로 이 챗GPT를 끊어버렸어요. 그래서 챗GPT가 안 열려요. 어, 그래서 어쨌든 내가 한국에 가서 챗GPT로 대화하면서 대화하는 거를 여러분들이랑 같이 보이고 디스커션 하도록 하겠습니다. Okay, well, I'll try to make it short class today. I'm trying to close today's class, only 1.5 hour. But I don't want to skip the class. So the okay, so this is the end of today's class, and then I will assign the homework as usual, and using the cutoff, and also I will try to upload the class note and also YouTube for the lecture note, and then assign the homework. Okay, thank you, and see you next week. Bye.